Have you ever considered what makes some of the universe's rules so steadfast, so unchanging, that they form the bedrock of all our understanding? Imagine a quality that persists no matter what transformations occur. In the realm of electrical engineering and physics, one such fundamental and unwavering rule is the principle of conservation of electric charge. Simply put, this principle states that the total electric charge within an isolated system remains constant. It can neither be created nor destroyed. It can only be transferred from one object or location to another. This foundational idea underpins our entire understanding of electricity and magnetism. The core mechanism behind this principle lies in the very nature of fundamental particles. Electric charge is an intrinsic property of matter, carried by particles such as electrons, which possess a negative charge, and protons, which have an equal but opposite positive charge. When we say charge is conserved, it means that if a system starts with a net charge, say positive 10 units, and nothing external adds or removes charge, then no matter how many interactions, rearrangements, or even nuclear reactions occur within that system, its total charge will always remain as positive 10 units. Charge is not an emergent property that can suddenly appear or disappear. It is always associated with specific particles that move or are rearranged. For example, when you rub a balloon on your hair, electrons are merely transferred from your hair to the balloon, making the balloon negatively charged and your hair positively charged. The sum of the charges remains zero as it was before the rubbing. This strict adherence to conservation is often linked to deep symmetries in nature, specifically a concept known as gauge invariance, which ensures the stability of electromagnetism. Understanding the conservation of electric charge is incredibly practical for anyone studying electrical phenomena. It forms the basis for Kirchhoff's current law, which states that the sum of currents entering a junction in a circuit must equal the sum of currents leaving it, essentially a statement of charge conservation over time. It helps us analyze electrostatic interactions, predicting how charges will redistribute on conductors or how static electricity accumulates and discharges. Furthermore, in the study of nuclear and particle physics, this principle is vital for balancing equations, ensuring that the total charge before and after a reaction, such as a radioactive decay or particle collision, remains precisely the same. This principle is not just a convenience. It is one of the most rigorously tested and universally upheld conservation laws in physics, alongside the conservation of energy and momentum. Its validity extends from the macroscopic world of electrical circuits down to the quantum realm of particle accelerators. One fascinating aspect is pair production, where a high-energy photon can transform into an electron and a positron, its antiparticle. Here, the net charge before, 0 for the photon, and after, -1 for the electron plus +1 for the positron, totaling 0, remains perfectly conserved. This illustrates that even when matter and antimatter are created or annihilated, the overarching principle of charge conservation holds true. The principle of conservation of electric charge is more than just a rule. It is a fundamental pillar upon which the entire edifice of electromagnetism stands. By recognizing that charge is a quantity that can only be transferred, never created or destroyed, you gain a powerful tool for analyzing circuits, understanding electrostatic phenomena, and predicting the outcomes of complex particle interactions. It provides a reliable framework for problem solving, ensuring consistency and accuracy in your understanding of how electrical systems behave.